Hello. So today we're going to be looking at variation and how it gets used in our math class. This is assignment 34, variation. And there are lots of different variation models, and you've actually been using them since Algebra 1, and you may or may not have actually learned that what you were doing was a variation model. It's just a way of classifying things and a way of explaining the relationship between input and output. Okay, so our first type is direct variation. And direct variation comes in the form of y equals kx. See that? That's called the constant of proportionality, or the constant of variation. And we'll see that k showing up in every one of our variation models. What language will clue you into the fact that you're supposed to be using this model? So we might have, sorry, I'm looking for something that's not an ultra fine point right now. Okay, we might see y varies directly with x, or we could see y is proportional to x. Language like that suggests to us that we're going to be using the direct variation model. Okay, and here's how it works. If I have if y equals 1/9 when x equals 3, and y varies directly with x, if I build the variation model, let's take that back and say I use direct variation when I see this language. The problems that we're going to run into, and that's why I want to erase this board and start a new board, the problems that we run into will sound like this. Y varies directly as x such at y equals 1/9 when x equals 3. 1. Find the variation constant. They could also ask for the constant proportionality, or they could ask for k. 2. Build the variation model, and then use that model to find y when x equals, and they'll just give you some number that x is equal to, or they may give you a number that y is equal to and ask you to find x, but when x is equal to blah blah blah. Alright, so we've got that, and let's actually do one x equals 6. Okay, so as far as finding the constant of variation, or the constant of proportionality, or the proportionality constant, as far as finding that, I plug in this given information into y equals kx. So I have 1/9 equals k times 3. And I want to find that variation constant, so I want to get k by itself. So I'm going to divide here by 3 on both sides. 3, 3. And so the k's cancel out on the right side, and on the left side, we have 1 over 27. K equals 1 over 27. Well, that's the first question. Find the constant of variation. The second says build the variation model. Well, remember y equals kx that we were talking about? Well, I'm just going to plug this k in there. And so now I have y equals 1 over 27x. That's building the variation model. And then finally, use the model to find y when x equals 6. All right, so y equals 1 over 27 times 6. And I can take out a 3 from both of those, and I get 2/9. So y will equal 2/9 when x equals 6. That's it. And you know, my experience is that with our in-class version of this day, that students feel really comfortable doing these problems by the end of class. So comfortable, in fact, that they don't study it for the unit quiz, and then they blow the questions on a quiz. But the variation questions are almost all like this, and like this in level of difficulty. Really, it's just a matter of identifying what type of variation model I should be using, finding that k with the given information, building the model, and then using the model. Okay? So let's look at another type of variation. Our next type of variation is direct variation as the nth power. Huh? Yeah, I feel you. Y equals x to the n is what we're talking about here. But remember, all of these variation models have a constant of variation. So here's ours. Okay. So this, in fact, I'm supposed to be writing. It's the problem when you color code things is you have to remember to keep switching colors. K, x to the n. Okay? And then what language will we hear for this? Well, I might hear something like y varies with the square root of x, or y is proportional to the cube of x. You know, something that suggests that there's a power involved. There's our model. And so what's a sample problem? Okay. The area of a circle, it varies with the square of its radius. Oh, well, I know that variation model. A equals kr squared. And then they'll give us some information to solve for k. In this case, let's say that area equals 36 pi when radius equals 6. So 36 pi. So we can plug these in, and what will that look like? Well, 36 pi equals k 6 squared. And so when I divide both sides by 6 squared, or 36, I get k equals pi. And is that surprising? Well, no. So there's our constant of proportionality. And then they'll ask me to build the model. There's the model, because I plugged the constant proportionality in. And finally, they're going to ask me to use the model. So find radius when area of the circle is 9 pi. So we'll plug in our area here. 9 pi equals pi r squared. I'm going to divide by pi then to get that r squared alone because they've asked us to solve for r. And so I see that 9 equals r squared. And we'll take the square root of each side. I know I'm supposed to have the plus and minus when I take the square root of each side, except that radius can never be negative, so I don't worry about that here. Okay, so there you go. That's this type of variation. The next one is indirect variation. Its model, y equals k over x, or k times 1 over x. I usually use this form, but this is legit too. And the language that we'll see here, y varies inversely with x, y is inversely proportional to x. That's the kind of language we're going to see. But what we do, it's pretty much the same stuff. So here's a sample question. They say y varies inversely with x such that y equals 6 if x equals 3. A, find the constant of variation. B, build the variation model. And then C, use the model to find y when x equals 36. All right, well, let's see about doing those. So find the constant of variation. So I know that we vary inversely, so we're using this model. I'm going to plug in this given information for x and y. 6 equals k over 3. So k equals 18. That's the constant of variation. Building the variation model, y equals 18 over x. Hey, so if on the quiz for this unit, I say find the constant of variation, and you write this, I mark it wrong, because this isn't the constant of variation. This is. Just that number is. That's the constant of variation. Don't give me the variation model when I'm looking for the constant of variation. The constant of variation is part of the variation model, but if you give me this when I ask for that, I think you don't know what the constant of variation is. So please make sure you answer the questions that are being asked. Finally, use this model to find y when x equals 36. So y equals 18 over 36, which reduces to 1/2. Y equals 1/2. Really, the problems are that easy. And I think, again, that's why people don't actually take notes on this stuff, which is why they don't study this stuff, and it's why they then forget all about it and bomb it on the quiz. So please make sure you know this. So then we have joint variation. And joint variation is where we vary depending on a couple of things, like we might see, for example, z varies jointly with x and y. So if I saw that kind of language, I'd have z equals kxy. And so now they're going to have to give me a little bit more information to solve k. Instead of giving me just one input and one output like the other variation models, they're going to need to give me a couple of inputs and an output to find that constant of variation. I might see z is jointly proportional to the square of x and the cube root of y. You know, something that combines the nth power thing that we were talking about before. And so what would this model look like? Z equals k x squared cube root of y. Yeah, they could actually say that too, where they don't give me the word joint, but they make it clear that z is proportional to this variable and this other variable. So if you don't see that word joint variation, it doesn't mean it's not joint variation. It just means that you might need to do a little more thinking about it. If you see that your output depends on two or more inputs, then you know it's joint variation and you build the model accordingly. So if I have the volume of cylinder is proportional to its height and the square of its base radius such that y equals 36 pi when r equals 2 and h equals 9. Period. Part A, find the variation constant to build the variation model. And then 3, find volume when r equals 9 and h equals 2. Okay, again, the same three questions get asked. Sometimes they ask all three, sometimes they ask only one of them. But these are pretty much the questions that we see over and over in these models. So let's see what we've got here. We've got volume proportional to height and the square of the radius. Volume equals proportional to height and radius squared. Cool. Well, let's plug in R, H, and V. 36 pi equals K times 9 times 2 squared. The squaring doesn't go here. The squaring is just on the 2. 4 times 9 is 36. I divide both sides by 36. That gives me K equals pi. Okay, so my variation model, V equals pi R squared H, is what you learned in middle school and again in geometry class. And then let's use this variation model to predict volume when radius is known and height is 2. So V equals pi 9 squared times 2, or 162 pi is the volume. Okay? So, these are all our variation models. Direct, joint, inverse, things raised to powers. And notice, I hope you noticed that we see so many of the things like direct variation, y equals kx. This is a linear model. It's the equation of any line through the origin. You've written lots of equations of lines through the origin, and you were doing direct variation then. Y equals k over x. Well, that's our rational function. We have it as one of our reference graphs. Y equals kx squared, or k square root of x. We feel like this is just a transformation of our reference graph. It could be that k equals 1, in which case we do get the reference graph. So we've had experience with all of these things. Even joint variation. Area of a triangle, 1/2 base times height. The area of a triangle is proportional to the base, the product of the base and the height. Or area of a circle. Area of a circle is proportional to the square of the radius. So many of the things that we've experienced as algebraic functions, even in other classes like geometry, we can describe using this variation language. Okay. All right, so let's move on, and let's ask this question. Let's say they don't tell me what variation model I should be using, but they give me a table. 5, 10, 15, 20, 25. 1, 1/2, 1/3, 1/4, 1/5. And they ask me, is this direct or inverse variation? And then they'll ask me, once I've determined which it is, to build that variation model. But let's think about how we could answer that question. Well, one way is, and my experience is that most students have a difficult time with this, is to look at the incremental change in the table and see what you see. So I know with direct variation, I should be going up by the same amount and here going down by the same amount. Well, I go down by 1/2, but then I don't go down by another 1/2. So I know that this is not direct variation by looking at the table and analyzing the differences from one ordered pair to the next. So the other one they gave me was y equals kx, and students have difficulty connecting this to a table. And we could take extra time to get you so that you were comfortable with it, but really I think an easier way is to say, look, you've been told that it's either y equals kx or y equals k over x. So this is what I'm going to recommend. So you can do it from the table. You could also do it graphically, right? If it's this, it makes the graph of a line. So here's 5, 10, 15, 20, and so we've got 1, we've got 1/2, we've got 1/3, we've got 1/4. Is that a linear model? No, I don't think that's a linear model. And so I can understand, in fact, it kind of looks like that rational function model, huh? Yeah, so we can understand that change and we could try and identify from the table or from the graph, but I probably would recommend that you just build the model. So let's say I think it's direct. So I'm going to plug in an ordered pair. 1/2 equals k times 10. So k equals 1/20. So y equals x 1/20 x. Okay, so I built this model based on this first ordered pair. Well, let's now plug in a different ordered pair, like the first one, and see if it's still true. 1/20 times 5. Well, I can cancel, and I get 1/4. Does 1/4 equal 1? No. So this can't be the model. Even though it's the model I build with an ordered pair from here, if all the other ordered pairs don't work in this model, i.e. the stuff on the left is equal to the stuff on the right, then that's not the model. So what would it have looked like if I had picked inverse? Well, I'd have 1/2 equals k/10. I would multiply both sides by 10. I would get 5 equals k. So I'd have y equals 5/x. Now let's plug in that first ordered pair again. Okay, I plug in a 1 and a 5. Oh look, 1 equals 1. That's great. What if I plug in a different ordered pair? What if I plug in 1/4 and 25/20? Well, 5 goes into 5 once, and 5 goes into 20 4 times, and I get 1/4. So this is inverse variation, and this is the specific inverse variation model. All right, so let's see how it goes for you. Okay. So now I have 10, 15, 20, 25. By the way, this sort of question, I've seen it show up on the ACT. They like asking about variation and giving you the table to figure it out. Okay, so what about some y values here? Well, I have 20, 16, 12, 8, and 4. Okay, so wow, that was really big, that's really small. Maybe I think it's inverse variation. So I build y equals k/x. And I plug an ordered pair in. 16 equals k/10. Multiply both sides by 10, k equals 160. So then our model would be 160/x. All right, let's put in another ordered pair. 8 equals 160/20. Wow, that did work. Huh, I wasn't expecting that. That's awkward. What if I plug in this one? 4 equals 160/25. Phew, that does not work. So 150 divided by 25 is 6. So this is 6 2/5, and that does not equal 4. So this is not an inverse variation model because this point clearly does not work in it. Well, is it direct variation? Y equals kx. So I'll plug in my 16 and my 10, and I'll get k equals 16/10, which reduces to 8/5. So y equals 8/5x. So let's plug in that ordered pair. 4 equals 8/. Am I missing something here? Oh, it's direct variation. Sorry. I was missing something is the answer. 8/5 times 25. Output is 16. I take a 2 out of each. That gives me my k. Input, output, input, output. that's 40. I feel like it's here. 16. These are going up by 5. These are going down by. Now I understand. Down by. So how do we get down by? Oh, this is interesting. Why can't k be negative? K should be able to be negative. Not all lines that go through the origin are positive, and this is certainly not decreasing. So how do I make that happen? It's very interesting. I'm sort of flummoxed. I know it's going down by this amount. 10, 16, and I need to divide by 10. I did. I take a 2 out of each of those and I get that. But that's not correct. Ugh. Y equals kx. So that yeah. I'm just completely flummoxed because oh, this doesn't does this doesn't pass through 0, 0. That's why that's not working. Because remember, this is the line that passes through 0, 0. So 5, 20, 10, 16, yeah, that's a problem. Oh, I'm sorry, I picked a bad problem for this. Well, don't use that one. I gotta cross it out of my notes. Okay, well, that was awkward. Quick, let's jump on to this other thing. Find the constant of proportionality. Okay, constant of proportionality in each case. First case, y is directly proportional to x and inversely proportional to the square of z if x equals 4 and z equals 3, then y equals 16. Okay, so let's see if we can find that constant proportionality. Y is directly proportional to x and inversely proportional to the square of z. Did you notice that I didn't do two separate y equals kx and y equals k over z squared? It's not two different things. I see that a lot in the quiz too. Y is directly proportional to x, kx, and inversely proportional to the square of z. So we know that goes on the bottom. Okay? If x equals 4 and z equals 3, y equals 16. Okay? 4, 3 squared. Okay, so that's going to be 9. I'm going to multiply both sides by 9, divide both sides by 4, and I end up with k equals 36. That's all we were asked to find, so that's all I'm going to find. Next, y is proportional to the square root of x and to the cube of z. If x equals 9 and z equals 2, then y equals 5. All right, well, let's see if we can find our constant of proportionality. Y is proportional to the square root of x and the cube of z. And then we'll plug in what we know. 5 equals k square root of 9 times 2. Square root of 9 is 3. 3 times 2 is 6, so I get 5 equals 6k, where k equals 5, 6. A common mistake on the quiz is for people to write 6/5 here. It might be worth your time to actually show the step where you divide by 6 on both sides. Now, because we've seen, I showed you some examples of how, you've been using variation models for a long time now. You'll actually run into some, I guess you want to call them word problems, but not really, because they sound like the other problems we've done in variation, but they're going to turn out to create, or they have real-world applications. So the intensity of illumination, that's how bright the thing is, from a light varies inversely as the square of the distance from the light source. Well, so what I think about here is the intensity is proportional to, varies inversely with, the square of the distance. Yeah, there you go. And then they'll give me some information, some knowledge about distance and intensity, and I'll be able to solve for k. Okay, how about this one? Let's take a look at Newton's gravitational force between two objects. So in the 1600s, when Newton's university was closed down because of plague, he came up with a whole bunch of stuff, including his inventing of the calculus and the laws of motion. So, this is a 21, 22-year-old Newton who created this little ditty. He said that the gravitational force F between two objects whose masses, I guess, because there's two of them, are m1 and m2, is proportional to the product of their masses and inversely with the square of the distance d between them. Okay, so, once you get past the place where you say, what? this guy came up for a way of figuring out what gravitational force would be between planets, and we're 300 years away from getting to another planet. Yeah, they didn't even have indoor plumbing really yet at this time. So what's he say? He says force is proportional to the product of the masses and inversely proportional to the square of the distance between them. There you go. Okie doke. So, when you do analyze the for variation, you'll probably find it pretty straightforward. So don't be scared. And really, all I want to say to you is, there's a worksheet. It's got lots of these wordy problems in it. Don't be scared about them. Just translate into your variation models. I look forward to hearing your questions from this section, and I'll see you in our next Zoom. Take care, everyone.